Welcome back, students. In my last video, I presented a simple five-stage pipeline. We have seen the data path and control, okay, for this simple pipeline. I also introduced three different types of hazards: structural, data, and control. In this video, I would like to talk about data hazards in detail and data forwarding between the different stages of a pipeline. First, let me define what a data hazard means. In programs, you can have data dependencies between instructions. So let me here use a highlighter, okay, to define what a data dependence means. So you can have, for example, two instructions, I and J, in which instruction I is going to write its result to a register, for example, R8. So the result of the add instruction will go to R8. And the next instruction, okay, so you have instruction J wants to read the value of R8. So clearly here we have a data dependence. So this is called read after write, because instruction J wants to read the value of R8, which is written by instruction I. So this is known as data dependence, okay, and instruction J depends on the result of instruction I. Now, why is it a data hazard? Okay, so the hazard occurs because of pipelining. Now, the problem is J, okay, wants to read R8, but it will read R8, okay, in the second stage of the pipeline. This is when the instruction J is going to read register R8. The problem is it's going to read R8 before it is written by instruction I. Remember that the write back stage is the last stage of the pipeline. It's stage number 5, as we have seen in the previous video. So if the instruction J reads R8, which is done during the second stage before it has been written, then this is the nature of the hazard. It's going to read the old value of R8, not the value that was computed by the add instruction. Let me give you an example about this. Here's an example of a read after write data hazard. In this example, there are 5 instructions. You can see that the subtract instruction is writing register R8. Okay, so the result is written in register R8. Notice that the next 4 instructions that appear after subtract, all of them want to read register R8. So all of them depend on the result of register R8. Now assume that for simplicity here in this example, I'm going to assume that the old value of register R8 is 10. Now the subtract instruction is going to go through the 5-stage pipeline, starting with the first stage, the instruction fetch stage. So the instruction will be fetched from the instruction cache. Then we read the source registers R9 and R13 from the register file. Then the instruction is executed. Then the 4th stage, it will bypass the 4th stage because it does not need data cache. And finally, it's going to write the result in the register file. So at clock cycle number 5, the instruction is going to write its result in the register file. However, the writing will happen at the edge of the clock at the end of clock cycle number 5. And the value will be available during clock cycle number 6. So suppose that the value that was computed by subtract is 20. So this is the new value of R8. This value is not available until clock number 6. Now, the add instruction is in the pipeline just immediately after the subtract instruction. So at clock cycle number 3, the add instruction has reached the second stage of the pipeline and it wants to read R8 from the register file. So which value is going to be read by the add instruction? It's going to be the old value. So the old value, which is 10, is read by the add instruction because the value has not been written yet by the subtract instruction. Remember that the write back stage is the last stage of the pipeline. Okay, so therefore the old value is read. Similarly, the OR instruction will read the value of register R8 from the register file at clock cycle 4 against the old value, which is read. You can see that the value, okay, of R8 is read before it has been written in the register file. What's interesting is the end instruction. The end instruction is going to read the value of R8 at clock cycle 5. Now, at clock cycle 5, two things are happening. The subtract instruction wants to write R8, and the end instruction wants to read R8. Now, which value is read by the end instruction? Is it the value which is the new value or the old value? Well, the answer is simple here. The answer will be the old value, which is 10, is read by the end instruction. So it's going to read the old value. Why? Because the new value has not been written yet. So the new value will be written at the end of clock cycle number 5, not at the beginning, at the end of clock cycle number 5, at the edge of the clock. So still the new value is still at the input of the register file. It has not really been written yet inside the register file. And the value which is read is at the output of the register file, which is the old value. So again, we have a problem with the end instruction. It's going to read the old value of R8. Now, how about the store instruction? The store instruction is going to read its value at clock cycle number 6. So you can see that at clock cycle number 6, okay, the store instruction is going to read the new value. So we don't really have a problem with the store instruction. So the problem is only with the next three instructions here, the add, the or, and the end. So these three instructions that appear immediately after the subtract instruction are going to read the old value of R8. And for this reason, we have this data hazard. So how does the pipeline handle data hazard? It cannot allow the add instruction to read R8 during clock cycle number 3. You can see that if it reads the value of R8 at clock cycle number 3, it's going to read the old value, as we have seen from the previous slide. So it has to wait. Simply, it has to wait until the subtract instruction writes the value of R8 in the register file. So until clock cycle number 6. It has to wait until clock cycle number 6. Then it can read the new value that was computed by the subtract instruction. Then it can read it from the register file. So this is one solution, which is called stalling the pipeline, which means that the add instruction is going to wait in the second stage of the pipeline. If it's going to wait in the second stage of the pipeline, it cannot read the R8 at clock cycle 3 or clock cycle 4 or clock cycle number 5, because if it does, then it's going to read the old value of R8. So it has to wait until clock cycle number 6. So there are three wasted clock cycles here, which is shown here as the three stall cycles. So during these three stall cycles, the add instruction is waiting in the second stage of the pipeline. It cannot really move into the execute stage. It cannot be allowed to execute. It cannot be allowed to read and execute during the next cycle. So during these three cycles, we cannot even fetch the next OR instruction, which is in memory. We have to wait until clock cycle number 6 to fetch the OR instruction from the instruction cache. Okay, so we have wasted here 3 clock cycles. Okay, this is the meaning of stalling the pipeline. Now it is safe at clock cycle number 6 for the add instruction to read R8 and then to proceed at clock cycle number 7 to execute the add instruction. At the same time, the OR instruction can be fetched from the instruction cache at clock cycle number 6, and then it can proceed to the second stage, in which it's going to read also R8 is going to be read by the OR instruction at clock cycle number 7. It's going to read the new value without causing any problem. So this solution is called stalling the pipeline. The problem of stalling the pipeline is that every time we have a data dependence, we are going to waste clock cycles. It's going to increase the execution time of the program. So this is not really a perfect solution, although it works, but it makes performance, it is going to reduce the performance of the pipeline. So we don't really want to reduce the performance. There is a better solution. Now, if you look at the subtract instruction is going to compute its value, its result, during clock cycle number 3. So it's going to execute on the ALU and produce its result at the end of clock cycle number 3. Now, because the result is available at the output of the ALU, there is no need to wait until clock cycle number 6 to read the value of R8 from the register file. So why not forwarding the ALU result back to the next instruction? So we can take the output of the ALU and we can feed it back to the input of the ALU. So this solution is called forwarding. So if the next instruction in memory depends on the subtract, if this instruction wants to read R8, which is going to be written by the subtract instruction, then we can use this technique, which is called forwarding, and we can use the output of the ALU and we can feed it back to the input of the ALU. Okay, it's a simple solution and it does not waste clock cycles. It does not stall the pipeline. So from the performance point of view, this is really an excellent solution. Let us take a look at the OR instruction. The OR instruction also depends on the subtract, but the OR instruction, by the time we are going to execute the OR instruction, the add instruction, okay, will be in the, so by the time the OR instruction has reached the second stage of the pipeline, it wants to read R8 from the register file. You can see that the subtract instruction, the ALU result, is now in the fourth stage of the pipeline. So we have to keep track. Where is the ALU result? And we have to forward the ALU result now from the fourth stage back into the ALU input. So it will be the second ALU input because now R8 is the second source register. It's not the first, it's the second source register. So we forward to the second input of the ALU. So now here we are forwarding from the memory stage back to the second input of the ALU. Now let us take a look at this AND instruction. I changed this AND instruction. So now this AND instruction is going to read R16 and R8. Now R16 is computed by the OR instruction. So therefore this AND instruction depends on the OR as well as on the subtract. So we have two data dependencies in this AND instruction. Again, we are going to use forwarding, but there are two forwardings. Now the ALU result for the subtract instruction, so the value is going to be written at the, it is now at the input. So at clock cycle number 5, the AND instruction is now in the second stage of the pipeline. If it reads R16 and R8, it's going to read the old value of R16 and the old value of R8. It's not the value that was computed by the OR instruction or the subtract instruction. So therefore, okay, what we have to do is that we have to forward the result of the R8, the result of the subtract instruction. So the result of the subtract instruction is now at the input of the register file at clock cycle number 5, and the result of the OR instruction is at the output of the ALU. So the ALU is executing the OR instruction. So we have to do here two forwardings. We have to forward from the input of the register file to the second input of the ALU. This will be the value of R8, and we have to forward also the output of the ALU, which is the value of R16, the value of the OR instruction, back to the first input of the ALU. So this technique is called forwarding the ALU result. So we can see that we can forward from 3 different stages. We can forward from the third stage, from the ALU stage, from the memory stage, and from the write back stage. So these are stages 3, 4, and 5. Let us see how forwarding can be implemented in the data path. Okay, so I'm going to focus here on the 3 stages of the pipeline. I'm going to focus on the second stage, which shows the register file. The third stage, which shows the ALU, as well as the fourth stage, which shows the data cache. Okay. Now, when we read from the register file, we read two source registers, okay? So we can actually get their values on bus A and bus B. But the values on bus A and bus B can be the old value of a register because the new value has not been updated yet inside the register file. So how can we implement forwarding? The way to do this is to introduce multiplexers, okay? So to introduce multiplexers at the A and B input, and we introduce a new buses that will connect the output of the ALU back to A and back to B, as well as the data from the fourth stage of the pipeline back to A and back to B, as well as the data which is the result, which is available on the bus W, okay, which is going to be written into the register file. So that this will be the input to the register file. So this result, which is written back into the register file, is also fed back to the A and B input. So these multiplexers are have four inputs, okay, so they can get their input from bus A and bus B. They can get their input from the result of the ALU. They can get the result from the fourth stage of the pipeline, as well as from the write back stage. Okay, so this is how we feed back the result back into the input A and B. So A and B here are used as inputs to the ALU. Now, because we are introducing multiplexers, we need to control these multiplexers. So for this reason, we need two control signals, which are called forward A and forward B. So let us take a look at the meaning of forward A and forward B in the next slide. Forward A and forward B can have four possible values. Now, 0 means that there is no forwarding. We are reading the value directly from the register file. In the case of forward A, it will be the value of register RS. In the case of register forward B, it will be the value of register RT. So the values are coming directly from the register file, and there is no forwarding. 1 means that we are forwarding the result of the previous instruction, which is still in the ALU stage. This is the case for forward A and for forward B. This, okay, for 2 means that we are forwarding the result of the second previous, and 3 means that we are forwarding the result of the third previous. The second previous will be in the memory stage. In the case of the third previous, it's coming from the write back stage. So this is the meaning of forward A and forward B. This is the meaning of these two control signals. Let us take a look at this example. It's a simple forwarding example. Now we have a sequence of 3 instructions: load word, or immediate, and subtract. Clearly, the subtract instruction depends on the load word, and it also depends on the or immediate. You can see R4 here. This shows that the subtract is reading R4, which is written by the load instruction. The subtract instruction is also reading R7, which is written by the or immediate. So we have two data dependencies. The subtract depends on the load word. The subtract also depends on the or immediate. Now, by the time we have fetched the subtract instruction, the subtract instruction will exist in the second stage of the pipeline. So here we have the subtract instruction, and this subtract instruction exists at the output of this instruction register. Now, at this cycle, once we have fetched the subtract instruction and it exists in the second stage of the pipeline, already we have the or immediate in the third stage of the pipeline, and we have the load instruction in the fourth stage of the pipeline. So if the current instruction exists in the second stage of the pipeline, then the previous instruction must be in the third stage, and the second previous must be in the fourth stage of the pipeline. Now, at this time, we can check if we have a data dependence. Clearly, the subtract instruction depends on the load, which is the second previous. So we must select forward A, okay, to be equal to 2. So forward A equal to 2, it means that it depends on the second previous instruction. Now the load instruction is going to load the data from the data cache. So the multiplexer is going to select the data from the data cache, and it's going to be forwarded back to A. So for this reason, forward A must be equal to 2 because we are forwarding the data from the memory stage back to A. In the case of forward B, let us take a look at forward B. What should be the value of forward B? What do you think should be the value of forward B? Well, look at the value of the second input here. So R7, the R7 here depends on the previous instruction, which is the OR immediate. So the OR immediate is now in the execute stage. Its result will be available at the output of the ALU. So forward B must be equal to just 1. Okay, it means that we are taking the output of the ALU and we are selecting it and making it as the value of B. Now notice that the subtract instruction is going to also to read the value of R7 and R4 and R7, okay, from the register file. Their values will be available on bus A and bus B, but these values are old values. We are not going to select them. We are not going to use them. So in all cases, we are going to read from the register file, but we are not going to use these values. So forward A equal to 2, it means that we are getting the value directly from the data cache and we are feeding it back to A. Forward B is equal to 1, it means that we are taking the output of the ALU and we are feeding it back to B. Now let us see how we can implement, okay, the forwarding. So now we have introduced the two control signals, forward A and forward B. We need to generate the values of these control signals. We need to produce the value of forward A and forward B. So we need a special logic, which is called the hazard detect logic. Okay, this hazard detect logic is in the second stage of the pipeline. The input here are RS and RT. These are the inputs, okay, to the hazard detect logic that will come directly from the instruction, which is in the decode stage, in the second stage of the pipeline. Now, RS and RT must be compared against RD2, RD3, and RD4. So we have to compare them against RD2, RD3, and RD4. These are the values of, these are the destination registers. These are the destination registers of the instructions that exist in the ALU stage and the execute stage. So RD2 is the destination register of the instruction, which is in the ALU stage. RD3 is the destination of the instruction, which is in the memory stage. And RD4 is the destination register of the instruction, which is in the write back stage. Also, we have to ensure that these instructions are going to write something into the register file. So we have the register write control signal that indicates that the instruction is going to write something into the register file. So register write 2, this means that we are going to write something to RD2. Register write 3 indicates that we are right. This is the register write control signal in the memory stage, indicating that we are going to write something to RD3. And register write 4, this is the register write control signal for RD4, indicating that we are going to write something in RD4. Because some instructions don't write anything, okay, the register write control signal might be 0. We have to ensure that the register write is 1. It means that we are going to write something into the register file. So all of these are now inputs into the hazard detect logic. Now, based on the values of these, then we can, this logic is going to produce, okay, it's going to produce forward A and forward B. Is going to produce these two control signals are going to control these two multiplexers at the input of A and B. So this is how we implement, this is how we detect hazards, and this is how we implement the forwarding logic. So we generate the control signals that will select what should be the input to A, okay, and what should be the input to B. Now let us write the equations, okay, the forwarding equations that will produce forward A and forward B. Remember that the current instruction, okay, which is being decoded, is in the second stage of the pipeline. This is the instruction decode stage. The previous instruction, okay, will be in the execute stage. The second previous will be in the memory stage, and the third previous will be in the write back stage. So what we have to do is that we have to check, okay, we have to check if RS is equal to RD2. If RS is equal to RD2, it indicates that the current instruction, which is being decoded, it depends on the previous instruction. Also, we must make sure that we are writing, okay, to RD2. So this is the register write control signal that indicates that we are writing to RD2. Now notice that RS must be different from 0, because in the case of register R0, it is hardwired to 0. So there is no need for forwarding if my source register is R0, okay? So RS must be different from 0 to indicate that, okay, we are not really reading register R0. So if this is the case, if this condition is true, then forward A will be equal to 1. That will be the value of forward A. Now this can be easily implemented by using 5-bit comparators, okay, that will compare the value of, so RS here and RD2, these are 5-bit register numbers. So we need actually a 5-bit comparator to compare, okay, the source register number here against the destination register number to indicate that we have a match. And we have an AND gate here that will end with the register write control signal. So this is just like a 3-input AND gate. And this RS different from R0. This is not really register 0. That can be detected using a NOR gate, a 5-input NOR gate, because this source register here is 5 bits. So if it is not 0, then it means that we are not really reading from source register R0. Okay, we can do the same thing here actually for RS, comparing RS against RD3. We can also compare it against RD4. We can check that we are writing here to register RD3. So this is register write 3 and this is register write 4. Okay, so if this is the case, we get forward A is equal to 2 and we get forward A is equal to 3. Now, if all of these conditions are false, then forward A will be equal to 0, indicating that there is no forwarding. Notice that it is written as an if-else statement. In other words, if more than one condition is true, we give priority, okay, to the first. So forward A is equal to 1 is given priority over 2 is given priority over 3, because we might have RS equal to RD2 and RD3 at the same time, or even RS equal to RD3 and RD4 at the same time. So it is actually based on this priority that we select the value of forward A. The same thing can be said about forward B, but we look at source register RT, not source register RS. So that's the difference between forward A and forward B. In the case of forward A, we are looking at RS. Okay, in the case of forward B, we are looking at the register RT. Okay, so this is how we write these equations, and these equations can be implemented very easily in logic. So we can convert these equations into logic, and we can implement this as a simple circuit that can generate the value of forward A and forward B. So this is how forwarding is implemented in the hardware. Okay, so this is the end of this video. In my next video, I will talk about the load instruction. Okay, the load instruction has a delay, and sometimes we cannot really forward the result directly from a load instruction to the next instruction if there is a data dependence. And I will talk about how to stall the pipeline. Okay, I will talk about how this can be implemented in the hardware. Thank you for watching.